So there are some other ideas in part 3 that I would like to mention before we go on to talking about hierarchical modeling. So I'm in part 3 of the PDF notes. There is some old material in here, and I don't want you to be misled by it. Someone asked a question during the break that makes me want to emphasize this. The very first kind of bugs that was ever built is that thing called, now called classic bugs, that was supposed to run only under Unix. And the process of doing MCMC sampling was so primitive in those days that they sometimes couldn't figure out how to sample from a particular distribution, and they had to discretize it. That sort of thing is long in the past, and we don't have to worry about those things anymore. As you can see by going into WinBugs, and then the same thing will be true in RJAGs as well. Always you have available to you quite a good set of information in the help section, the basic user manual, and when you click on something like the distributions, you get another window, and it knows about how to use each of these distributions either as a prior or as a sampling distribution. So it knows Bernoulli, binomial, categorical, negative binomial, Poisson, beta, chi-square, double exponential, exponential gamma, generalized gamma, log normal, logistic, normal, Pareto, T, uniform, and Weibull, and it has a quite modest set of multivariate distributions. It knows about the multinomial as a generalization of the binomial and Bernoulli story, the Dirichlet as a generalization of the beta distribution. We'll talk more about that later. And the multivariate normal, multivariate student T, and Wishart distributions. That's about all it knows. But that's practically everything that people use in regular modeling. And if you have new distributions for either for prior or for sampling that you want to use, it can, the language accommodates that. For example, if you click on the tricks advanced use of the language, there's a section on specifying a new sampling distribution, how to create that out of whole cloth, how to create a new prior distribution that's not listed in their set of distributions, and so on. Another resource I draw your attention to is that under the help pull-down menu, there are wide variety of examples. And so one of the fastest ways to learn a wide variety of Bayesian modeling is to go through all of the examples in Volume 1 and Volume 2. So borrow a Windows machine from somebody if you don't have one, and just spend time going through the examples in here, because they've got, by now they have a repertoire of something like 50 examples from a very wide variety of disciplines, and it covers things all the way up from fairly simple applications of Bayesian modeling to quite complicated ones. And of course, these sorts of examples are vital for us to know about, because they can serve as templates. And your problem, you may discover that there's a problem you're working on now that's a lot like one of the ones in here, and so you do the usual thing that we all do for learning, especially when writing code. For example, you find some code that someone else has written that's similar to what you want to do, and you modify it, right? So this is a treasure of correct examples worked out so that you can use them as templates to build upon in your own work. Let me show you how to do the doodlebug thing. For this purpose, I have a new handout, which we will go through now. I'll go ahead and grab this and put it in another notepad file. So I'm going to show you now how to construct a graphical model version of the NB10 model that we did. And so step one, you're in WinBugs, and there's a doodle menu. So it says from the doodle menu, select new. And basically, these little things that they're asking you to specify describe trivial aspects of things like how big the window is and so on, I just let them all default. So we're going to go ahead and hit OK. So now we have a model window that we're going to try to build a graphical model in. Put the mouse arrow in the middle of the untitled window. This is this new thing. Hold down the Control key and left click. This will create a plate that corresponds to the likelihood loop for the model. So I showed you that these graphical models have things that act like pages in a book, and each page stands for I equals 1, 2, dot, 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 down to n in the likelihood repetition or the sampling distribution repetition. So put the mouse arrow in the middle of the untitled window, hold down the Control key and left click. So let's do that. Middle, hold down the Control key and left click. And now it understands that we want to build one of these for loops that constructs the sampling distribution and therefore the likelihood function. Next, WinBugs is waiting for you to fill in the looping index, for which you may as well type in the lowercase letter I. So you see up there it is blinking at me, so I type in the lowercase letter I. And then I left click on the from to tell it where from and where to. So from 1, and I left click up to and used a number like little n, for example, the value that I used before. So now it knows that the likelihood or sampling distribution loop is supposed to run from 1 to n, as I runs from 1 to n. That's good. Now position the mouse arrow in the middle of the plate and left click to create a stochastic node that corresponds to the data values. So position the mouse arrow in the middle of the plate, left click to create a stochastic node. In the middle of the plate, left click, and this is now going to be our node for the data. And as soon as the node comes up, it wants to know, as you can see, what the name is, what the type is, what is the sampling distribution, and what are the parameters of that sampling distribution. So under name colon, we can type y sub I or y of I. So up here, I type y open bracket, I close bracket. And then left click on density. This will create a pull down menu of possible sampling distributions. So left click on density, and you see there's a bunch of different distributions. And one of the ones, the one I want for my sampling model here is DT. And so if it will ever actually, that was weird, if it'll ever actually let me go there, good. Then it wants to know what parameters of the T distribution, what's the mean, what's the precision, what's the degrees of freedom. And so in each case, I don't like 0.0. I want to put an actual variable name in there. So left click on the mean, use the backspace key to erase the 0.0 and type the actual thing we want there, namely mu. Left click on mean, use the backspace arrow to get rid of the 0.0 and type in mu. Left click on precision, take away what's there and type in tau. Left click on degrees of freedom, take away what's there and type in nu. So now we've specified that the sampling distribution involves the y sub i's are IID, conditionally IID from a T distribution with mean mu, precision tau, and degrees of freedom nu as I runs from 1 to n. Now, somewhere outside the plate, in other words, let's use, for instance, somewhere to the left of it, let's left click to create a new stochastic node. Basically what we're going to do is we're going to tell it now that so I left click out here and I get a new node. And we're going to tell it how to specify the prior distribution for each of the parameters that are in the sampling distribution and likelihood function. So let's make this first one mu. So up there in the name where it's waiting for you to put in something, I type in mu. And in this case, I want mu to have a normal prior distribution with mean 0 and small precision and no left or right truncations for lower or upper bound. So that particular node is finished. Then I want to create another node for tau. So somewhere else outside the plate, I left click again to get another node. And this one here I'm going to call tau. And I want its density to be, for instance, the one we used was the gamma epsilon density for that. So I'll go density d gamma. And it turns out that the default choices inside WinBugs are the same gamma epsilon that we talked about before. So that finishes the prior on tau. And then finally do the same thing for new. Left click somewhere out here, call it new, and regard it as a uniform. So here I'm going to want to go density and use D uniform. And right away it's going to say what's the lower bound and what's the upper bound. So I left click on lower bound and say that the lower bound is 2.0 and the upper bound is 12.0. So now, basically, I have the model quite well defined, except I haven't told the WinBugs yet about how the y sub i's depend on these things. And essentially, what we're going to want to do now is to establish the dependencies between the prior parameters and the sampling distribution by means of what are called directed arrows in directed nodes, directed links in the graph that are illustrated by arrows. And that's what's basically going to say, once we get done putting these arrows in here, there's going to be an arrow from mu to y sub I and from tau to y sub I and from nu to y sub I. And that reflects the fact that if you were trying to generate a random y sub I, first you would, from this model, first you would generate a mu, generate a tau, generate a nu, and then that would tell you what t distribution you should be sampling from.
It doesn't know already that the y sub i's have those, a dt of that, so it doesn't know what direction to go. But
it probably should know at this point. It probably should know what to do. You're right. But just to pin things down, they want you to actually put in the arrows that define the nature of the stochastic dependence. So to do this, left click on the y sub I node, and then hold the control key down and left click on the mu node. So left click on the y sub I node, hold the control key down, and left click on the mu node. And now that creates the directed link between them. So again, left click on Y, hold the control key down and left click on tau. Left click on Y, hold the control key down and left click on nu. And the model's finished. That's the model that we were using. It does not allow me yet to generate other quantities which are dependent upon this, but the basic model has been created now, and we're done basically. So let's see if there was anything else down here. And to generate the algebraic version of the model, foreground your graphical model window, and then go back to the doodle menu and select write code, and that will write the code out. So I make sure this window is foregrounded. I go back to the doodle menu and choose write code, and a new little window pops up in which the algebraic version of the model is stored. So if you prefer to think in terms of these directed graphs, which clearly the WinBugs people do, because if you look in the examples manual and pick one of the examples, they write the model down, well, they do it both ways generally. They write it down in algebraic fashion, and then they always show you what the graphical model looks like, which in some cases can be quite complicated, as you can see. So you can think about it either way. And you can see that this is the same model that we used before, except they're using a syntax model semicolon and then left and curly right braces. That whole thing could be deleted. And then there's nothing in there about the other quantities I want to monitor. They have chosen to put the likelihood / sampling loop first and the prior stuff below it. But as I mentioned to you last time, that's entirely arbitrary. You can put them in any order you like as long as you don't put the stuff that's not part of the loop inside the loop. That would be tempting fate, shall we say. And so if I wanted to continue with other things, now that I've got the algebraic version, I could start typing in other nodes in the graph that I want to monitor, for example, y.nu and sigma and so on, and then there I'd be. So that's how to use doodlebugs. And that pretty well exhausts the extent of my knowledge about that aspect of the WinBugs world. Okay, so this stuff about how to run classic bugs, probably no one in here is that interested in, because you aren't going to be running bugs on a Unix machine, probably. I have some motivation in here for why I chose the particular diffuse priors that I chose. So let's look at that for a second. We want to express the idea that we don't know much about mu, and so a standard way to do that for something that lives on the whole real line is to give it, as I mentioned briefly last time, but let's think it through again this time, a normal prior with a mean of 0 and a really, really small precision. So a precision on the order of 1 times 10 to the minus 6. That means a variance of 1,000,000 and therefore a standard deviation of 1,000. So this is like saying before any data arrived, I was prepared to think of mu as a number anywhere from about minus 3,000 to plus 3,000. And in the little narrow range where the likelihood is appreciable, even though globally that normal distribution is highly nonlinear, locally in the little region in which I'm interested in finding the likelihood to be appreciable, locally it'll be highly linear. So here's a picture that shows you that. I'll come back to these other details in a minute. So check it out. If I plot that normal from minus 3,000 to 3,000, of course it's highly nonlinear, it's highly curvy across the whole range, but the likelihood turns out to be appreciable just from about 402 to 407, and so I replot the same normal density from 402 to 407, and it's a straight line that's practically horizontal, practically uniform. So in effect, this is Taylor's theorem in action, right? Every nice function is locally linear. It might be globally curvy, but it's locally linear to constant and linear terms in the Taylor series. So in effect, we're using Taylor's theorem in a useful way to create a diffuse prior by choosing a distribution that is very much highly informative if mu, in fact, the likelihood were appreciable from, let's say, minus 6,000 to plus 6,000. That would be a highly informative prior for that, because it would say that we're pretty sure in the prior that mu is actually only between minus 3,000 and 3,000. But if the data says that mu is probably somewhere around 400 with a little narrow band in it, then using a prior like this is going to create just exactly the kind of diffuseness that I want. So similarly, I want a diffuse prior for sigma squared, or equivalently for its reciprocal, the precision. And we've talked already about the idea of using the gamma epsilon epsilon prior for something that lives on the positive part of the real line. So we could try this story that I've shown you in the code. That tau is like a draw from a gamma distribution with parameters epsilon and epsilon for epsilon equal to 0.001. And I've shown you a picture of this before. It's close to flat over an extremely broad range. Here I've drawn the gamma epsilon epsilon distribution for you over the range from approximately 0 up to about 2. And now we can use standard frequentist calculations to work out where the likelihood is going to be appreciable for the sigma squared parameter. So let's see. First of all, we know that how I understood that the likelihood would be appreciable for mu between 402 and 407. If we were fitting a Gaussian model to the data, then the 95% confidence interval is just start at the mean and go 2 standard errors either way, where each standard error behaves like S over the square root of n, right? So this tells me that 2 standard errors either way looks like running from 403 to 406, and so by the empirical rule, almost all of the likelihood would be non-negligible in the region that involves going 3 standard errors either way, and that goes down to about 402 and up to about 407. So I'm just using the empirical rule. For sigma squared, you can use the standard frequentist result that in repeated sampling across multiple data sets, n-1 times the ordinary sample variance over the population variance behaves like a chi-square draw on n-1 degrees of freedom. And in the frequentist way of looking at it, S squared is random and sigma squared is fixed. And so Mr. Neyman uses that to create another one of his confidence tricks. He can then write a frequentist statement that the random variable n-1 S squared over sigma squared lies between capital A and capital B with some probability like 0.99, where capital A and capital B are chosen to be places on the chi-square curve with n-1 degrees of freedom that have hardly any area to the left and to the right of them. And now Neyman's confidence trick works by taking that statement, which is a valid frequentist probability statement in which S squared is random and sigma squared is fixed, and rearranging it to make it look like it's a probability statement about the parameter, which you're not allowed to do in the frequentist approach, but it gives him a highly suggestive way of figuring out what he should use for his confidence interval. Because now that we have this thing looking like a Bayesian probability statement for sigma squared, why not just use this number here on the left as your left endpoint of your confidence interval, and the number over here on the right as your right endpoint of the confidence interval. So that's Neyman's confidence trick as usual. And when I plug that in with the data, I go ahead and stick the data values in R and work out the details of that by getting the length and putting that in n, and the variance and putting it in s squared, and getting the quantiles from the chi-square, the low and the high end of things, and I calculate the endpoints. And so it runs from about 29.8 to about 62.2. And then, because that's a confidence interval for the variance, the corresponding confidence interval for the precision would be found just by taking the reciprocal of those endpoints. So 1 over 62 is about 0.016, and 1 over 29 is about 0.033. So that tells me that the likelihood should be appreciable for tau roughly in the region from about 0.015 to maybe 0.035. And so I plotted that for you here. And I've replotted the gamma prior distribution in this little range here, and you can see that indeed it is pretty close to uniform across that range. It's got a little bit of, tiny bit of tilt back towards smaller values, so the prior would be tugging very gently in the direction of a smaller value of tau than what the data might indicate, but that's a quite trivial effect. And now, as far as the prior on the degrees of freedom are concerned, as I told you, I just used a uniform prior where I picked the bottom edge to be 2 because I don't believe in going below 2 degrees of freedom in the T family. And I picked 12 as a value that it looked to me as though it did not truncate the likelihood function over there on the right tail. Some of you guys noticed that maybe I should have gone out a little farther, but no problem there. And you can ignore this paragraph because you're not going to be using classic bugs. And so for initial values, why not start the chain off at the sample mean from U? And so why not start for nu at some value in the middle, somewhere between 2 and 12? So I just took 5. And then there's a formula from the T family that I showed you before that says that the variance of a draw from a T curve with parameters mu and sigma squared and nu is sigma squared over times nu over nu minus 2. So you can stick in 5 and equate that to the sample variance and figure out the tau should be somewhere around 0.04. And so those are going to be my starting values. And so then we're off to the races, and I showed you how to do the actual run. Again, you can ignore this classic bug stuff. If you're interested, I'm not going to focus on it too much here. There's a broad set of MCMC diagnostics that are available to see things like take a little preliminary run and have it estimate for you how long the burn-in should really be. Take a little preliminary run and have it estimate for you how long the monitoring run should be, things of that kind. They've all been collected into a set of CODA functions, rather R functions called CODA. And so you can download the CODA package the same way we downloaded the RJAGS package and explore it. So one of them that's in there is by a guy called John Gavecki, and he tries to figure out whether you actually have stationarity. I'll skip that for now. One of them is about looking for the possibility of multiple modes using this Gelman-Rubin thing. This is an old idea that people don't use very much anymore, but there's a simple diagnostic that helps to work out how large the burn-in and the monitoring period should be. And again, you can read that for yourself. And this is a diagnostic that's borrowed from the stochastic simulation, the applied probability literature to work out whether your chain has reached stationarity or not with the iterations you've got. And then, of course, plotting the autocorrelations is a good thing, and looking at their values. Cross correlations of 2-time series are just like what you would think of doing you make a column of the values of one of the series at a particular time, and the other column is the other series at time t plus k or t minus k, and you can create a sense of cross correlation at lag k between 2 series. That's almost never useful, but it's in there in the CODA package. And then there's a variety. I've shown you how to make these MCMC4 plots, so you know about everything that's going on in there. And I've already told you about this business about the variance inflation factor, which gave us our Monte Carlo standard error. And then I show you some results from the WinBugs implementation. And there's an interesting punchline here, which I will get to in the minute. If you incorrectly fit a Gaussian model to this data set, and we know that that's a bad model because we can see for ourselves that the Pasteur distribution on the degrees of freedom is concentrated down on very small values. and you know the Gaussian is like a T on very large degrees of freedom, so we can tell from our fitting the bigger model, the T model, that the Gaussian is wrong. But an interesting thing happens. There's a little table I think I have here, or at least I'm showing you the comparison. The estimate of the true weight of NB10 in the Gaussian and the T models is about the same, but the posterior standard deviation from the T model is about 40% smaller than the posterior standard deviation from the Gaussian model. And so interestingly, this is an example where we are being rewarded for the virtue of having fit a better model to the data. We actually get a narrower uncertainty band than what comes out of the Gaussian. And there's a reason for that. You remember we talked when we were speaking about maximum likelihood about this concept called observed information, otherwise known as Fisher information, that measures, in some sense, how much you have learned about the parameter from the data set. And it's related to the posterior variance for in many parametric problems. It turns out you can prove a theorem that shows that among all symmetric distributions that are unimodal and that live on the whole real line, the Gaussian is the one that has the smallest amount of information, Fisher information, for finding the center of symmetry. And so, weirdly enough, for all those years in the history of statistics when no one could fit anything other than Gaussian models to data because they didn't know how to do the fitting, weirdly enough, throughout that period, they were actually doing something that was slightly protective. They were using models that produced uncertainty bands, namely the Gaussian, that were wider than would actually be the right uncertainty bands if you used the correct non-Gaussian distribution. So that's a kind of a strange fact in the history of statistics that because the normal distribution has minimal Fisher information for the location parameter, it's actually to use it instead of the right model is usually a conservative action rather than one that is liberal. And for those of you who know about the concept of entropy, this is related to the fact that the Gaussian has maximal entropy among all symmetric unimodal distributions on on the real line as well. This is interesting because what just happened is actually a little bit of a surprise. If we pretended we knew that the data were Gaussian, that's like saying that we knew that the right model is a T distribution with very large degrees of freedom. For example, T on infinite degrees of freedom, or T on 500 is already pretty close to infinite, and so on. That's like pretending that we are prepared to fit the T model with known degrees of freedom, and that gives a standard error of about 0.65 for the thing we care about. If instead we try to be more honest about what we know and don't know, and relax that model and embed the Gaussian model in a bigger model of which it's a special case, namely the T model with unknown degrees of freedom, then I think you'd agree with me that we have just admitted a net increase in uncertainty, because previously we pretended we knew that the degrees of freedom parameter was infinite, or at least very big, and now we don't know what it is. We're going to ask the data. So there's been a net increase in uncertainty. You could even call it a net increase in model uncertainty, because you're going from a Gaussian model to a T model that's more uncertain in terms of not knowing the third parameter. And yet, the net increase in model uncertainty was accompanied in this problem with a net decrease in the uncertainty about the thing we care about. And that's pretty cool. It doesn't happen very often. Usually when model uncertainty increases, so does inferential uncertainty, and I've written about this before. And it happens in this case because two things happen together. Firstly, the T model fits better than the Gaussian, as I've mentioned to you already. And secondly, the Gaussian is a conservative model as far as inferential accuracy for location parameters is concerned because of that property of minimal Fisher information. And there's a thing here about how to download CODA, but you know how to do that already. So that finishes part 3 of the lecture notes. And it brings us to a point where we can now start a new unit of material, namely hierarchical and mixture modeling. So let me get this onto the desktop. And I'd like to begin with a case study in which the ideas unfold a bit more simply than some of the ones we'll cover later on. This first unit is about hierarchical models for combining information. And this sort of model is of direct relevance here in the Valley because you guys are running A/B trials all the time where A serves as treatment, let's say, and B serves as control. And in fact, one way to increase your accuracy with which you're making the comparison is if it turns out that in your judgment you have the possibility of other data sets that could serve also as controls, for instance. And so imagine an experiment that has one treatment group but 4 or 5 different control groups, for example, all expected to be somewhat similar to each other in their approximately having the same conditions, namely approximately control conditions. Then this is a way to combine information across those control groups to create a synthesis of that information that will yield sharper inferences than if you only had one control group. So this use of hierarchical modeling is to combine information across similar studies of the same phenomenon. And the unit of science in which this arose is the discipline of meta-analysis. There are 2 main disciplines in which this idea of meta-analysis has been used a lot. One is medicine, and the other is education. And the reason it was invented for those disciplines is that in both cases, the manner in which research is funded in both medicine and education in this country is the following. A relatively large number of people are each given in parallel a relatively small amount of money to try to answer a particular question. This is not necessarily a very good way to do science. In fact, if there were such a thing as a kind of research czar and you trusted this person enough, it would probably be better to try to come up with one big experiment that was run really well by really high quality people and be done with it. But that's not how money is given out by agencies like the NSF. Instead, they tend to give out smaller chunks of money to a bunch of people to do things that are similar to each other. And so at one level, this is a good thing because science needs a degree of replicability. When you find something that you think is a truth about the world that no one had noticed before, everybody who cares about your result, a lot of people should immediately go out and try to replicate it. And this is a kind of forced replication at the design level rather than than an optional replication after someone has tried to announce something. Cold fusion, remember that some years ago, where those guys from Utah or wherever they were claimed that they could create the process of fusion, the same process that powers the sun and other stars, at room temperature, rather than only being able to do it at extraordinarily high temperatures. And of course, as soon as they announced that, dozens of people around the world rushed right out and tried to replicate their findings and were unable to replicate, and thereby science ended up deciding that there was no such thing as cold fusion. So here, this is from medicine. Anyway, if you're in a realm where there's a whole bunch of small studies of something, then you certainly need a way to combine all those small studies into a kind of not just an analysis, but a meta-analysis, a synthesis of all the information from all the studies combined to produce an answer that's better than what you would get from any one of the studies by itself. That's essentially what the discipline of meta-analysis is about. And so some years ago, someone had a theory that if you focused on patients who had already had a heart attack and you gave them a small dose of aspirin every day, that would actually help to prevent their future death. And the clinical theory on which this is based is that aspirin is a blood thinner, and one of the main ways that you can die subsequent to a heart attack is to have either a second heart attack or a stroke because a blood clot was created in your heart as part of the process of having the heart attack. And the blood clot can either go to your brain and create a stroke, or it can go out of your body, out of your heart and come back into your heart in another part of the heart and create another heart attack. So why not give people a small dose of something that thins the blood and see if it works? There was no other natural treatment that was second best to that with respect to giving someone a pill at the time. And so they had a treatment group that got aspirin, and they had a control group that got placebo, so an inert pill that looked just like the aspirin pill. And they randomized, in each of the studies I'm about to show you the data from, they randomized people 50% chance of being in the aspirin group, 50% chance of being in the placebo group. And the data, instead of studying this phenomenon once, it was studied 6 times by people from a variety of different countries. And the summary, table 5.1 there, summarizes the results from the 6 studies that we're going to meta-analyze here. So let's look at study UK-1, the first study in the table. There were 615 patients in the aspirin group, and they had a mortality rate over a suitable period of time after taking aspirin for a long enough period of time for it to actually have a chance to work. They had a mortality rate of about 8%. And the placebo group consisted of about the same number of people, 624, and their mortality rate was sharply higher, almost 11%. Would you think that a difference in mortality rates between 10.74% and 7.97% would be large in practical terms? Would that be a difference that's big enough to matter clinically? It's a home run, actually. It's a big difference. That would translate into a lot of people not dying. Similarly, CDPA, the second study, had 758 patients, and their mortality rate was about 6% in the aspirin group against 771 in the placebo group, and their rate was 8.3%. Again, 8.3 is noticeably higher than 5.8 by an amount that's large in practical terms. In fact, as you go along down this table, all 5 of the first 5 studies there show that aspirin appears to have acted in a cause and effect way, because it was a randomized controlled trial, at least on the patients in these studies. It had a causal effect of making mortality go down by on the order of about 1.5 to 2 percentage points. But then along comes this study called AMOS that was much larger than all the other ones. Look how the AMOS study had 2,200 patients in treatment and 2,200 patients in control. And they found an 11% mortality rate in aspirin and a 10% mortality rate in placebo. In other words, they're the biggest study of all, and they got a result that it went in the opposite direction to all the other results. Well, what the hell? You know, what do we do now? In particular, if you were a doctor who had a patient like this, who just had a heart attack, and you were trying to digest this information and decide what to do, would it be better to give that patient aspirin or not? So essentially what we want to do is to combine the information from those 6 studies to get an overall sense of what's going on that accounts properly for all the variability that's actually here. Notice there's something curious about the first 5 studies, though. All 5 of them go in the same direction, and all 5 of them have an additive effect, meaning subtracting placebo mortality rate minus aspirin of about the same order of magnitude, about 1.5 to 3 percentage points, something like that. But if they were supposed to be studies, parallel studies of the same exact treatment, presumably with similar patient cohorts, then why did one of them have an aspirin mortality rate of 5.8% and another one have an aspirin mortality rate of 12.26%? Would you agree that difference was large in practical terms? It's enormous. It's even bigger than the difference between treatment and control. And it begs, and it sort of shouts at us from this table, why is it that even though these top 5 studies there were supposed to be studying the same thing, why did they get about the same additive effect, but why, that's fine, but why did they have such wildly different mortality rates in the aspirin group? And maybe even worse, why were the mortality rates in the placebo group so wildly different, from 8.3% all the way up to 14.82%? Well, okay, and so scientifically, what's going on here is that there may have been small differences in the treatment protocols, and you always try to find out what those exact protocols were and make sure that you can try to adjust for them in whatever way is appropriate. For example, did they all use the same dose of aspirin? Did they all have everybody in the aspirin group take the aspirin for the same number of days before monitoring them to see what the death rate was? Did they all monitor the people to look at their death rate for the same amount of time after they stopped taking aspirin? These are all parts of the protocols, and you'd want to make sure those were the same or similar, and adjust for them accordingly if not. That turns out to not have been the problem here. The treatment protocols were all relatively similar, but just as this gentleman says, if you're going to try to do an experiment like this, what you should really do to really fully generalize to everybody in the world with a heart attack is somehow figure out a way to take a sample of people who are about to be randomized either to treatment or control. The original sample before the randomization should be like a random sample from everybody in the world who's had a heart attack. And no one can actually do that in practice, right? Imagine there isn't any roster anywhere of everybody in the world who's had a heart attack that you could write as one big list and choose a random set of rows from that list, and then try to enroll all those people in the 200 countries they would be in, right? Try to enroll all those people into your study. That's just not how it's done. So instead, what everybody does is they try to get people who they judge to be representative of everybody with heart attack, and then they randomize those people into the experiment. This is quite relevant to those of you in the Valley who are doing the AB stuff as well, because it bears directly on what would serve as an appropriate alternative control group, right? Because if you use what's going on with one particular version of your website, for example, at a particular period of time, is a somewhat similar version of the website at a slightly different time, is that good enough to be similar, to correspond to an actual control group that's similar enough that you could imagine combining them in an appropriate way? Those are all judgment calls in the same way that people use judgment to try to get patient cohorts that were similar. But you can see that they clearly did not get patient cohorts that were similar. To have a control group mortality rate difference that ran from 8.3% up to 14.8% means that they did not get patient cohorts that were similar. So we need Amos, I don't remember the details. I can track that down for you.
Okay, but if your hospital quality rate varied in these different geographic locations, maybe where Amos was held, like more people died, right? So it sort of moved up susceptibility, and so.
But still, you have some explaining to do, because maybe more people died there, but why did even more people die in the aspirin group than the placebo group? I mean, that requires some fast talking, right? So, well, UK-1 and 2, I think we're British studies. I think. We can track that down. Some of you could look on your favorite browser and help us with that if you wanted to try. Anyway, what is the appropriate way to combine these data sets to get an overall story of what's going on? Here is a quite naive thing to do. Take all the aspirin people here. I'll make a little schematic of it. Well, first I'll say, here is a thing to do, and then you guys can tell me why it's naive. So I'm going to have one enormous big treatment group and one enormous big control group. So this is treatment, this is control. And I'll just take all 615 of those patients from UK1 and stack them there, and all 624 of these patients over here from UK1 and stack them there. And then I'll just take all those 758 patients in the treatment group from CDPA. There were 758 of them right there, stack them there. And there were 771 over here from CDPA in the control group, and so on. Just stack them all together into one big long vector for treatment and one big long vector for control, and then do your favorite method of comparing two independent samples. Is that a method for combining information across the studies? Undoubtedly. Why is it a naive method for doing so? Pardon? When we're done, we're about to ignore these labels right here. We have them in the data set originally, but we're about to ignore them and just analyze these things here. Well, what's the usual analysis? It assumes that the treatment numbers are conditionally IID from exactly the same data, exactly the same sampling distribution, and the control numbers are conditionally IID from exactly the same sampling distribution that might be different from the treatment one. And we can see with our own eyes back here in this table that that would be an extraordinarily naive thing to assume, because right there in front of us, we have sharp differences in mortality rates across the across all 6 studies. So this method over here, let's agree to call this method naive pooling. And this is a terrible idea. So let's not do that. Instead, we have to come up with something better. Here's something that people used to do at the early days of meta-analysis. In the very early days of this, meta-analysis was dominated by frequentists. And frequentists are people who like to look at p-values. And I'll have quite a bit more to say later on. Have I already? Yes, I already had one unit, didn't I? In dispraise of hypothesis testing. But here's p-values. So one thing you could do is you could calculate y sub I, which is the difference in the direction it looks like placebo minus aspirin mortality rate. So in the UK-1 study, 10.74 minus 7.97 turns out to be 2.77 percentage points. So you could calculate the difference in each study. That gets you that column there called y sub I. You could use standard frequentist methods to work out the standard error of that difference. And let's see if we can remind ourselves of how that works. I'll try to use this one, I think. Let's talk about the standard error in any one study. Standard error of t-bar. T-bar is the average in, I'll call it n sub t in the treatment group, of all the y sub i's. We'll call them y sub ij's. This is patient in any one study I, patient j in study I. And I guess this needs to be 1 over n sub t sub I. And each of those things is a 1 or a 0. So this is a kind of this is sort of a p hat for treatment. So we could call it standard error, estimated standard error of p hat for treatment in study I. And you remember probably how that works. Maybe we even talked about it earlier in the frequentist part of things. That has its usual formula. You go p hat times 1 minus p hat over how many people there are. So p hat t sub I times 1 minus that same guy, 1 minus p hat t sub I over n sub t sub I. So that's our usual square root of pq over n kind of thing, right, from Bernoulli data. So that's the standard error in the treatment group. Similarly, the standard error in the control group, SE hat C bar, SE hat P hat sub T in control group I. It looks the same way except it has a C in it instead of a T. So P hat C sub I, 1 minus P hat C sub I over N C sub I. All right, that's good. But now, does anybody remember how uncertainty combines when we're interested in creating the quantity T bar minus C bar, and the two things T bar and C bar are independent of each other? Anybody recall how that goes? So now what we want is the estimated standard error of T bar minus C bar, where each of these things is independent of each other thing because we ran an independent samples, 2 independent samples sort of story. Another name for it would be SE hat of that P hat T, T sub I bar minus C sub I bar. T sub I minus, I guess I should have done it over here, T sub I and C sub I minus P hat control I. Ring any bells? It's a basic formula, and the basic idea is this. Uncertainty about a difference or a sum when you're working with independent quantities combines like the hypotenuse of a right triangle. Remember this? So you put the estimated standard error of one of the things on one leg and the estimated standard error of the other thing on the other leg. and then the estimated standard error of the difference is equal to the hypotenuse of that right triangle. P hat T sub I minus P hat C sub I. So this is going to be equal to, with Pythagoras, this squared plus this squared equals this squared, right? And so I can get the square root of the sum of the squares of those guys there. So it's going to be the square root of the sum of the squares, P hat T sub I squared plus SE hat P hat C sub I. And that, using that previous formula, is going to look like this. It's just going to go square root of P hat T sub I 1 minus P hat T sub I over N T sub I plus P hat C sub I 1 minus P hat C sub I over N C sub I. So that's this thing here that I'm going to call square root of V sub I in the thing I'm about to show you on the screen. That's the standard error of the difference expressed in percentage points. So that's this column in the comparison table at the bottom here of this page. That's the column called square root of V. Those are the standard errors. And so what we learn, among other things, and it's an unpleasant truth, is that even with 615 patients in UK1 in the treatment group and 624 in the control group, so that the estimated difference is 2.77, the standard error for that estimated difference is still quite large. It's still 1.65 percentage points, because the 0-1 outcome scale, yes, no, did the person die or not, is a relatively information-poor scale. Instead of getting your information on a continuous gray scale, if all you get is a yes or a no, you have to have a lot more data to understand what's going on. And so, unfortunately, this, if you were one of these stat sig people, in the usual frequentist way, UK-1 would just barely be statistically significant if you were allowed to look only in one direction in the standard way. You'd calculate a z statistic, you'd go difference divided by its standard error, and this 2.77 turns out to be about 1.7 times larger than its standard error. And if you made the argument to yourself before the experiment began that there's no way that aspirin could make things worse, having not seen the Amos results, then you would be prepared to calculate what the frequentists call a one-tailed p-value from a one-sided test. You'd only look in the direction where it looked as though the null is that aspirin had no effect, and the alternative is that aspirin made things better. And that would give you a one-sided or one-tailed p-value of 0.047. And glory be, you can now publish, because the one-tailed p-value is below the magic number 0.05, and now you can publish. Of course, maybe one of the referees would point out that your two-tailed p-value is 0.094, and that's bigger than 0.05. And why did you decide that one-tailed was right, and so maybe you shouldn't publish? And that's all just crap, right? If you were prepared to be convinced by a one-tailed p-value of 0.047, you should be essentially equally convinced by a two-tailed p-value of twice that. So that's neither here nor there. But so you do this thing over and over again 6 times. You get the difference in the standard error and the z ratio and the p-value. And then Fisher, who loved p-values, who was the one who invented them, Fisher developed decades ago a method for combining p-values across experiments. He does not get a combined p-value of 0.072. That's not where this number came from. This number came from doing the naive pooling approach. You just toss all the data into one big pile. The overall difference is about 0.9 percentage point with a standard error of about 0.6 percentage point, and that gives rise to an overall p-value from the naive pooled approach of 0.072. I don't remember what Fisher's method gives on this problem for combining p-values, but I'm not that interested in it because for the reasons I told you before. The p-value story is really not where we want to be, because the answer is coming out on the artificial probability scale, not on the scale of the data. What we care about is how many percentage points of mortality did things get better or worse, give or take how much. So we want our answers to come out on the scale of the data, not on the artificial p-value scale. Okay, so not a very satisfactory summary of what's going on to to pool all these groups together, all these studies together. Not a very satisfying solution to do something that involves pooling the p-values. We got to do something better. In fact, the first 5 trials together give an improvement of about 2.3 percentage points, which is a 20% drop from the weighted average placebo mortality of 11.5%. And that is really big in clinical terms. When you can actually make mortality go down by even 4 or 5%, and I don't mean 4 or 5 percentage points, I mean 4 or 5%. You know how when you're comparing 2%, you can talk about the relative difference between those percents by going bigger percent minus smaller percent over smaller percent, and you get a relative change. And this is something that the newscasters on the radio and TV and the newspapers get wrong all the time. If a death rate goes from 5% to 4%, people talk the people on TV talk about that as a 1% difference in mortality, when what it is a 1 percentage point difference in mortality, and it actually represents a 20% drop in mortality from 5% to 4%. So it's perfectly fine for us to compare 2 percentages in relative terms, and this turns out to be a 20% drop in mortality. That would be big. If you're in the hospital biz or in general in the trying to keep patients from dying unnecessarily biz, that would be big. But then Amos went the other way. So here are some questions. Why did Amos get such different results? Secondly, what should we do next to reduce our uncertainty about the answer to question 1? And thirdly, and perhaps even more importantly, if you were a doctor treating a patient like those eligible for the trials in that table, what therapy should you employ while the answers to those first 2 questions are sought? And so if I were to paraphrase question 3, here's a different version of it, question 4. How should the information from these 6 experiments be combined to produce a more informative summary than those obtained from each experiment by itself? And that, in the one sentence, is the discipline of meta-analysis, how to do that. And so you got your frequentist meta-analysts who combine the p-values, like I said, and that's not going to be good enough. So let's try to do something better. And what I'm about to show you has both Bayesian and frequentist versions to it, but I'm going to also show you that the Bayesian version often produces better answers when even regarded from a frequentist point of view. In other words, the intervals you get from the Bayesian story actually have better coverage property than the intervals that you get from the frequentist approach. When you do it right, with the right priors in the Bayesian approach, your 95% intervals for what the truth is that's going on here cover the truth close to 95%, and the frequentist intervals might only cover the truth 65% of the time or 80% of the time. So this is one of these places where it's sharply better to be a Bayesian than to do a frequentist analysis. And the principal reason is as follows. And this kind of data, if you've never worked with this kind of data before, it has a variety of surprises in it. The total number of patients in these 6 trials combined is in excess of 10,000. In fact, it's pushing 11,000. Is this a large data set or a small data set? At the patient level, it's an enormous data set. But for some purposes, the thing that drives it is not how many total patients there are, but how many total studies there are. Because we're going to have to estimate between study variation, and that's like having a sample of size 6. And so the right answer to my question is that it was improper of me to draw your attention only to the 11,000 number. For some questions, the effective sample size of this entire meta-experiment is 11,000. For other questions, the effective sample size of this meta-experiment is 6. And for yet other questions, it's somewhere in between those 2 extremes. So with hierarchical data, this is an example of hierarchical data. We have studies at the top level of a little tree and patients nested within each study, because each patient in this table here was enrolled into one and only one study. And so in the jargon of analysis of variance, study acts as a clustering or a clustering sort of effect, and patients are nested inside study. That makes the data set have a hierarchical character, and we're about to build a hierarchical model to capture that. And so the reason that the Bayesian methods work quite a bit better is that they do better jobs in small sample data sets than frequentist methods do. And believe it or not, this data set with 11,000 patients in it is a small sample data set with respect to variation between the studies. So here's a better model. Let's see, we're supposed to take our next break at 2:30, and it appears to be 2:30. So I guess we'll take our break, and I'll explain this model to you when we get back.